My name is Pranavi. I am from CIC section. My roll number is 45. I am going to deliver a seminar on dielectrics. Electric dipole moment. The product of charge and the distance between the two charges, it is called as electric dipole moment. Consider a charge q. Here plus q is the positive charge and minus q is the negative charge. The distance between the two charges is small r. Mu is equal to q into small r. Therefore, the units for the electric dipole moment mu is dpi. Coming to consider a parallel plate capacitor having two charges, one is positive charge and another one is negative charge. The distance between these two charges is capital D. Here we are applying an electric field that is capital E. From this, D is directly proportional to capital E. D is equal to epsilon into capital E in medium, whereas D is equal to epsilon naught into capital E plus P, that is polarized polarity, in vacuum. From this, Xi is equal to epsilon or minus 1. Here, without an electric field, the dipoles are arranged in random direction. When we apply an electric field, the dipoles are arranged in a particular direction, that is the direction of electric field. Electric susceptibility Xi. The electric susceptibility Xi, it is defined as the ratio of polarization vector to the applied electric field, that is capital E. From this, Xi is equal to P whole divided by capital E, where P is equal to Xi into capital E. Xi is equal to epsilon or minus 1. Xi, that is susceptibility, it has no units. Various polarization process. When the specimen is placed inside a DC electric field, the polarization is due to 4 types of process: electronic polarization, ionic polarization, orientation polarization, and space charge polarization. Coming to electronic polarization. When an electric field is applied to an atom, the positively charged nucleus, it displays in the direction of field and E. It could be in opposite direction, and this kind of displacement, it will produce an electric dipole within the atom. That is, dipole moment is proportional to the magnitude of the field strength, that is capital E. Mu E is proportional to capital E. From this, mu E is equal to proportionality constant alpha E into capital E. Here alpha E is the electronic polarizability constant. This kind of polarization is mostly exhibited in monoatomic gases like helium, neon, argon, krypton, xenon, and it increases with increase of volume of the atom. It occurs only at optical frequencies, that is 10 power 15 Hz, and it is independent of temperature. Coming to the derivation part, let sigma be the charge density of the sphere. Sigma is equal to minus z into E whole divided by 4 by 3rd pi r cube. Here minus Ze, it represents the total charge in the sphere. Thus, the negative charge in the sphere of the radius x is QE is equal to sigma into 4 by 3rd pi x cube. By substituting the sigma value, we get QE is equal to minus Z into E whole divided by 4 by 3rd pi into r cube into 4 by 3rd pi x cube. From this, QE is equal to minus Z into E whole divided by capital R cube into x cube. Consider it as first equation. Now, Fc is equal to 1 by 4 pi epsilon naught into QE into QP whole divided by x square. From this 1 by 4 pi epsilon naught into x square into, we know the QE value, that is minus Z into E into x cube whole divided by capital R cube, and QP is equal to ZE. From this, Fc is equal to minus Z square E square x whole divided by 4 pi epsilon naught into capital R cube. Consider it as second equation. The force experienced by the displaced nucleus in EF of strength E is FL is equal to capital E into Q, that is equal to Z into E into capital E. Consider it as third equation. FL is equal to Fc. From this, minus Z square E square x whole divided by 4 pi epsilon naught into capital R cube is equal to Z into small e into capital E. From this, minus Z into Ex whole divided by 4 pi epsilon naught into capital R cube into capital E. We know the formula capital E is equal to dipole moment whole divided by alpha E. Here dipole moment is equal to mu is equal to minus z into Ex. By substituting the E value in the above equation, we get minus z into Ex whole divided by 4 pi epsilon naught into capital R cube is equal to minus z into Ex whole divided by alpha E. From this, alpha E is equal to 4 pi epsilon naught into capital R cube. Hence, the electronic polarizability is directly proportional to the cube of the radius of the atom, that is capital R cube. Here alpha E is the electronic polarizability and 4 pi epsilon naught is the proportionality constant. This is about electronic polarization. Coming to ionic polarization. The ionic polarization, it occurs when the atoms they form the molecules, and it is mainly due to a relative displacement of the atomic components of the molecule in the presence of an electric field. When an electric field is applied to the molecule, the positive ions they displaced by the x1 to the negative side electric field, and the negative ions are displaced by the x2 to the positive side of the field. Therefore, the resultant dipole moment mu is equal to q into x1 plus x2. Restoring force constant F, it depends upon the mass of the ion and natural frequency, and it is given by F is equal to small e into capital E, that is equal to m into omega naught square into x. From this, x is equal to E into capital E whole divided by m into omega naught square. Therefore, x1 plus x2 is equal to E into capital E whole divided by omega naught square into 1 by small m plus 1 by capital M, where capital M is the mass of anion and small m is the mass of cation. Mu ionic is equal to E into x1 plus x2 is equal to E square E whole divided by omega naught square into 1 by small m plus 1 by capital M. From this, alpha ionic is equal to mu ionic whole divided by capital E. By substituting mu ionic formula in the above alpha ionic, from this alpha ionic is equal to E square whole divided by omega naught square into 1 by small m plus 1 by capital M. This is all about ionic polarization. It is a slower process when compared to electronic polarization. This polarization, it occurs at the frequency 10 power 13 Hz, and it is independent of temperature. Coming to Lorentz field or internal field. In a dielectric, it is the space and time average of the electric field intensity acting on a particular molecule in the dielectric material. Evaluation of internal electric field. Here we are considering a dielectric material which is placed between the parallel plate capacitors, and here A is the atom which is surrounded by a spherical quantity. Here we are getting the four electric fields as E1, E2, E3 and E4. Field 1. E1 is the field intensity at capital A. It is due to the charge density on the plates. E1 is equal to capital D whole divided by epsilon naught. We know that capital D is equal to epsilon naught into capital E plus P. From this, by substituting D value E1 into epsilon naught in the above equation, we get E1 is equal to epsilon naught into capital E plus P whole divided by epsilon naught. From this, E1 is equal to capital E plus P whole divided by epsilon naught. Consider it as first equation. Coming to field E2. E2 is the field intensity at capital A. It is due to the charge density induced on the two sides of the dielectric. E2 is equal to minus P whole divided by epsilon naught. Consider it as second equation. E3. It is the field intensity at capital A due to the atoms contained in the cavity. We are assuming a cubic structure. So, E3 equal to 0. Field E4. This is due to the polarized charges on the surface of the spherical cavity, we know that dA is equal to 2 pi into PQ into Q into capital R. From this dA is equal to 2 pi R sin theta into R d theta. dA is equal to 2 pi R square sin theta d theta, where dA is the surface area between theta and theta plus d theta. The field due to this charge at capital A, which is denoted by dE4, and it is given by dE4 is equal to 1 by 4 pi epsilon naught into dq whole divided by r square. The field in theta equal to 0 direction, dE4 is equal to 1 by 4 pi epsilon naught into dq cos theta whole divided by r square. dE4 is equal to 1 by 4 pi epsilon naught into r square into 2 pi r square p cos theta sin theta d theta into cos theta. From this dE4 is equal to p whole divided by 2 epsilon naught into cos square theta into sin theta into d theta. Thus, the total field E4 is due to the charges on the surface of the entire cavity, that is E4 equal to integral 0 to pi dE4 integral 0 to pi p whole divided by 2 epsilon naught into cos square theta into sin theta d theta. By keeping the constant aside, that is p whole divided by 2 epsilon naught, integral of 0 to pi cos square theta sin theta d theta. Let x is equal to cos theta and dx is equal to minus sin theta into d theta, and by evaluating the integral, that is integral of 0 to pi cos square theta sin theta d theta, that is p whole divided by 2 epsilon naught into integral 1 to minus 1 x square dx. From this, minus p whole divided by 2 epsilon naught into x cube whole divided by 3, that is from 1 to minus 1. By substituting minus 1 and 1 values, we get E4 is equal to p whole divided by 3 into epsilon naught. This is the fourth electric field E4. The internal field or Lorentz field, it can be written as EI is equal to E1 plus E2 plus E3 plus E4. From this, EI is equal to E plus P whole divided by epsilon naught minus P whole divided by epsilon naught plus 0 plus P whole divided by 3 epsilon naught. And we get the internal electric field EI is equal to E plus P whole divided by 3 epsilon naught. What is Clausius-Massotti relation? Here we are considering a dielectric material having the cubic structure and assume the ionic polarizability alpha I and orientational polarizability alpha O is equal to 0. We know the formula polarization P is equal to capital N into mu. Here mu is equal to alpha E into EI, because alpha I and alpha O equal to 0. By substituting the mu value in P, from this P is equal to N into alpha E into EI, where EI is equal to E plus P whole divided by 3 epsilon naught, that is the internal electric field or Lorentz field. P is equal to N alpha E into EI. By substituting EI value, P is equal to N alpha E into E plus P whole divided by 3 epsilon naught. From this, P is equal to N into alpha E into capital E plus N into alpha E into P whole divided by 3 epsilon naught. From this, P minus N into alpha E into P whole divided by 3 epsilon naught is equal to N into alpha E into capital E. By taking the common as P into 1 minus N alpha E whole divided by 3 epsilon naught equal to N into alpha E into capital E. From this, P is equal to N into alpha E into capital E whole divided by 1 minus N into alpha E whole divided by 3 epsilon naught. Consider it as first equation. We know that the polarization vector P is equal to epsilon naught into capital E into epsilon r minus 1. Consider it as second equation. From equation 1 and 2, equate the P values. N alpha E capital E whole divided by 1 minus N alpha E whole divided by 3 epsilon naught equal to epsilon naught into capital E into epsilon r minus 1. From this, 1 minus N alpha E whole divided by 3 epsilon naught is equal to n alpha E capital E whole divided by epsilon naught into capital E into epsilon or minus 1. From this 1 minus n alpha E whole divided by 3 epsilon naught equal to n alpha E whole divided by epsilon naught into epsilon or minus 1. From this 1 is equal to n alpha E whole divided by 3 epsilon naught plus n alpha E whole divided by epsilon naught into epsilon or minus 1. By taking the common as n alpha E whole divided by 3 epsilon naught into 1 plus 3 whole divided by epsilon or minus 1 equal to 1. n alpha E whole divided by 3 epsilon naught equal to 1 whole divided by 1 plus 3 whole divided by epsilon or minus 1. From this n alpha E whole divided by 3 epsilon naught equal to epsilon r minus 1 whole divided by epsilon r plus 2. This is the Clausius-Massotti relation. Coming to ferroelectric materials or ferroelectricity. These ferroelectric crystals, it exhibit the spontaneous polarization, that is an electric polarization without electric field. These crystals possess high dielectric constant. The each unit cell of a ferroelectric crystal, it carries a reversible electric dipole moment. Examples of this are sodium nitrate NaNO3, barium titanate BaTiO3, etc. Solid dielectric in transformers. The fibrous materials that are used in air-cooled transformers. The cotton tape is used for insulating the conductors of oil-cooled transformers. High quality synthetic resin bonded paper in the form of cylinders is used as an insulator between the core and the coils and also between the primary and the secondary windings. The pressboard or the press paper, it is used as a filling and as a packing material between the coil. This is all about the dielectrics. Thank you, ma'am. Thank you for giving me this opportunity.